Now let's nerd out with one of Carly's favorite problems in all of statistics. So what's your favorite problem?
So my favorite problem is called the birthday problem. And this is a great problem that we love to do in a big group of people. So the question is, if we have 100 people in a room, what's the probability that at least 2 of them share a birthday?
So I'm going to dissect this problem and lay out a few assumptions before we dive into it to make it easier to actually calculate using simulation, because we don't have 100 people here to ask 100 different people what their birthday is. And we want to simulate this for lots and lots of groups of 100 people, because we might see an anomaly. We might just get lucky if there's 2 people that have birthdays on January 1st or something.
Exactly.
So I'm going to make the assumption that there's exactly 365 days in the year, that there's no leap year, and I'm going to also assume that every single birthday is equally likely. And that statistically we say that birthdays are uniformly distributed, that there is an equal probability of being born on January 1st, 2nd, 3rd, 4th, even though that's actually not ends up being the case. And the simulation, we're going to actually count out the number of people who are needed for a double birthday to happen, because then that's going to allow us, that's an easier simulation to do, because that gets an actual number, and then we can get a probability of how many times is that less than 100 people in the room. So the simulation should count the number of people up to and including the person with the repeated birthday. So if you think about, if both of our birthdays were January 1st, then we'd say that there only needs to be 2 people in the room for a shared birthday.
Exactly.
So that's going to be how we count our answer out. So part 1 is we're going to write a simulation to simulate trying to the birthday problem a total of 1,000 times. So we want to try the birthday problem 1,000 times. And we're going to use a function find birthday count that returns the number of people that have needed to have a duplicate birthday. And we're going to program find birthday count later. So what we're going to do is we're going to basically just write the simulation, assuming that we have a function called find birthday count that's going to do all the hard math for us. So I'm going to go ahead and just write my simple simulation. So data is equal to square bracket for I in range 1,000. And then I'm going to say people is equal to find birthday count, open close. So this function is going to find the number of people I need to have a duplicate birthday, which if we were birth January 1st, it'd be 2, so we count both of us. And that will be in the people variable. I'm going to accumulate that variable. So D is equal to people colon people, and then, curly brace, and then data dot append of D, and then finally df is equal to pd dot data frame of data. And here, if we were to just run this code, we would see at least 2 errors, because the first thing I see is we don't have PD defined.
Right.
So Carly's going to import pandas as PD.
Import pandas.
And while you're there, you might as well import random, because we know we're going to need it. And then even now, if we run this code, you should still see another error.
Let's see, it's running really quick. And I do see another error. It says find birthday count is not defined.
And that's exactly what we expect, because we've never defined what's in find birthday count. So the second part of this problem is write a find birthday function that always returns 50. That allows us to actually simulate something. So this should get our simulation work. We know that the result's not finally 50, but this is a common programming technique of to put in the function that does something, and then we're going to come back and actually make it work later. Make it correct. It's going to work, but it's not going to make it correct. So we're going to come back and make it correct later. So to write a function, we're going to use def find birthday count, making sure the capitalization, the parentheses, everything about it, it's the exact same as we used in the simulation itself.
Yes.
Because it's a control flow statement, it ends with a colon. So def find control count, colon, and then inside of this function, we're going to indent out, and we're going to simply return 50. So this should, once we have this line, now we can go back and rerun our original simulation.
Sounds good.
And when we run our original simulation, what, do you get an error anymore?
No, no error.
Awesome, and let's go ahead and look at our data frame and see what we get.
So our data frame has 1,000 rows, one column called people.
Awesome, and what's the result of that column?
All 50s.
All 50. So our data frame has all 50s. So this is almost what we want to do. We have a data frame that's simulated 1,000 times, but we said there's always 50 people needed in the room. So is that what we want?
No.
So the simulation doesn't need to be touched though. The simulation's perfect. Now we just need to actually make this find birthday count function actually work. So now let's think about how you might approach the problem. There's a lot of ways to approach this problem. So Carly, how would you think about this problem? Do you have a...
So if I was thinking about solving this problem, I would think about going person by person, basically having 100 people line them up and ask the first person, when's your birthday? And then the second person and the third person, and then stopping when I get a match to any of the previous people.
Okay, so one thing we can do is we can accumulate data inside, we can basically add data to a data frame and then see if we ever get a match where that person number's there. Okay, so I like this, and this can definitely work. So what we can do is our algorithm is basically going to be loop through at least, I'm going to say loop through 365 people. And then we are going to go to, with Carly's algorithm, we're going to ask each one their birthday.
Yep.
And then we're going to stop when a repeat occurs.
And count how many people.
Right, and we're going to see where we were at to that
Yes.
point. So let's go ahead and try and do this approach.
Okay.
So this sounds great, and then I'm going to also go through an approach that I would take as a kind of more of a computer scientist that takes a kind of very mathematical approach to this that does it completely differently. So in Carly's approach, we're just going to, so this is all going to be inside the function def find birthday count. So everything we're writing is inside this function, so everything we're writing is going to be indented over once. And what we're going to do is I'm going to say for I in range 365, because we know that, I'm actually going to say 366, because we know that by the time you get to 366 days, somebody is guaranteed to have an overlapping birthday.
Exactly. That would be if every person, even if every person had a different birthday up until then, the 366 person has to overlap.
Yeah, so this is the, so this is kind of where how long we want the computer to work before it basically gives up. And so for I in range 366, and we're going to say birthday is equal to random.randint 1,365. So we're going to randomly generate a number between 1 to 365, and we said the birthdays were uniformly distributed. So this is basically 1 is January 1st, 2 is January 2nd, and so forth. And then what we'll do is, because this is we're basically building a simulation, before this for loop, we even need to have this data is equal to an empty list. And we're going to go ahead and now accumulate birthday inside D. D is equal to curly bracket birthday colon birthday. And then we can say data.append D. And now we're going to do something we haven't done before. So we're going to change things up a little bit. And we don't normally do this because creating a data frame is kind of an expensive operation on a computer. It takes a lot of time. So we're going to actually, right after data.append, inside the loop, we're going to go ahead and make a data frame out of it right away. So we're always going to make a new data frame every time we see it. So I'm going to say df is equal to pd.dataframe of data. And now I have a new data frame every single time I get to this point. And what that means is that my first time I have a data frame which is one record, then 2, then 3, then 4. And what I want to see is if there is at least, so I've added my birthday, which is a 1, and your birthday, which is a 1. So if we have an overlap, how many birthdays should be the same as my birthday?
At least 1.
Not just 1, but we have a duplicate, so we need 2, right?
Oh, for each of us.
Yeah,
yes.
because I just added you. You were the second person. You're also a 1. So I'm going to have a variable called overlap that's going to check what is the length of the number of people who has an overlap with the current birthday. So I'm going to say length is equal, or overlap is equal to length, parentheses, of the data frame where we're selecting the rows data frame dot birthday is double equal to birthday. So how many records in my data frame has the same birthday as me? So this is basically just like what you said, that you're going to ask every single person their birthday, and you're going to check, has that birthday been told by somebody else?
Got it.
So if you hear the number 20, basically January 20th, the second person to say January 20th, now in the data frame we have 2 20s recorded. So that's where we see 2. So if we say if overlap is double equal to 2, so the second time, as soon as we see a second overlap, we're going to return the length of the data frame, which is how many people we asked. So length of the entire data frame. So what we have is we've got this simulation that's now returning inside of the simulation. What return will do is return will get out of that function as soon as we see the return value. And then I just often like to make sure that every single function has a return at the very end. So now if we go outside the for loop and outside of the if statement, so at the very end, only indented once, I go ahead and say return -1 if we get out of the for loop. So this means we never found a duplicate. We should never, ever, ever get to -1. But this will give, if we ever see -1 in the data set, we'll know something went wrong.
Got it.
And this gives me an assurance that even if I'm not 100% sure this code's doing exactly what it's doing, then if I see a -1, I know something went wrong and I need to actually go back and look at it. So, and this is particularly useful because like I'm just writing this code here, Carly's typing it up. I'm not even 100% sure that Carly's got every bit of syntax, even though she knows Python. She might have typed something wrong. So this gives us assurance that if something goes wrong, we're actually able to identify the error. So def find birthday count.
So now run.
Let's go ahead and see what's in the simulation. Yeah.
Okay.
Let's not even worry about the function by itself.
So do I go to?
Let's just type out df and let's see what's in our data frame.
Yes. So it looks like we have 1,000 rows and it just says people and then there's a bunch of numbers.
And what are the numbers?
34, 25, 22, 9, 19, 38, 40, 26.
Oh, interesting. So Carly, those are really small numbers.
Yeah, so remember this is telling us, this variable people is telling us how many people we need to ask before we get a duplicate birthday.
So really, could you just ask 9 people?
That's what happened one time. There were 9 people. We only asked 9 people and we already found a duplicate. The highest number is 40.
So that seems incredibly small.
Yeah.
There are only 40 people. So one thing I like to do is look at the distribution of that result. So a histogram is a great tool to look at the distribution of the results. So if you just do df.hist, Carly, or df.plot.hist, either one works, what do you get?
Need to remember my open close parentheses at
Yes,
the end.
df.hist
and
open
I
close.
get a histogram that is slightly skewed to the right, kind of centered around between 20 and 30.
Yeah, so this is a gorgeous histogram. We see that there's a peak of the histogram, and yeah, I see that there's basically bars increasing, increasing, increasing. We got the top bar, third one over, and then sort of almost symmetrical, but a long tail off the right-hand side.
Yes.
And so this is going to be, the total area of the histogram is going to be 100% of the people. So one thing we can say is how many people needs to be in the room for it to be about equally likely, 50% of the people, to have a birthday?
Only.
Looking just at the histogram, like where can we divide about half the area? Just an estimation.
Oh, like the median.
Yeah.
Got it. That is right around, I'd say like 25.
So about 25. And now this gives us a great point that we can start seeing if this is right. So let's see if we just simply say df at df.birthday is greater than equal, or sorry, less than or equal to 25 or fewer people, we should guess that there's going to be about, what the simulation ran, 1,000 times?
Yes.
So
it's df at df.people.
about people, yes, because we're looking at, right.
Got an error. Let's see. 572 rows.
572, so that's a little bit more than half.
Yeah.
So a little bit more than half the simulations, there were 25 or fewer people needed before we got a double birthday. So let's bring that down to like 24, 23.
Yeah. I'll do 24, and that is 544.
544 is 24.
23 is 519. 22 is 474.
474. So in this simulation, we saw that somewhere between 22 and 23 people are needed for half of the time for you to have somebody in that room sharing a birthday.
Yeah.
And does that correspond with the result you've seen classically in this problem?
Yeah, this problem is actually most people, if you have them kind of guess what you think the probability is at the beginning, they'll say a lower number. And if we have 100 people in a room, the probability of having at least one match of birthdays, if we actually figure this out using statistics, we can use one of our special cases for at least one match. We actually get that the probability is over 99%. It's really close to 100% if we have 100 people in a room.
And we can see this in the simulation by writing one final Python statement that says, let's see if anyone was 100 people or more. So df at df.people is greater than or equal to 100. Is going to be every case where we had to have 100 people in the room before a duplicate.
And nothing there.
Never happened.
That never happened.
So we know that, so by looking at this histogram, we know that 50% of people had 22, or 50% of simulations, had 22 or fewer people to get a double birthday. So this is a fantastic result of a complicated problem. We now have simulated the fact that there's lots of people who come into a room and look at having a birthday. And one thing that, and I promised you one bit, and that bit is how I might approach the problem the first time I see this problem, because I think Carly's approach is really nice and really understandable. But you can also look at this problem by thinking about this function as if the first person is assumed to have the birthday of 1, and the second birthday, no matter what birthday they have, is the birthday 2, you simply are randomizing a number and seeing if the random number is ever smaller than the number of people already seen before. Because it doesn't actually matter what your birthday is. You can say the first unique birthday is number 1. And then the second person, if their birthday was 1 as well in a random number sense, then it's an overlap statistically.
That's a good way to think about it too.
And so once you have 10 people, you say, okay, your birthday 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And only if that 11th person gets a number 11 or greater, does that simulation then say we keep going?
Exactly.
So that's a more mathematical way of thinking about simulation where you don't have to run that data frame. And you saw this took a little bit of time to run when you ran Carly's way. And that's because we generated, let's say, 1,000 simulations, an average of about 23 birthdays. So 1,000 times 23, 23,000 data frames were generated by the computer. So it was a lot of data that was generated just to figure out the problem. So sometimes we think about these problems more mathematically, but both ways get the result. And for small problems, just work on what's most logical to you. Because it's more important to get the result. We can always turn down the simulation just 100 runs if it runs too slow, and then bump it up to like 10,000 to run for a whole hour while we grab lunch.
Yep.